Let's talk about support vector machines for doing classification and for doing regression. So support vector machines are a relatively new technique for doing these tasks. They were invented in the 80s and at the time really revolutionized the field because it was a brand new way of approaching the problem. It had some appealing mathematical properties and it actually showed that it had some pretty good performance too. Now, contrary to the name, support vector machines really have nothing to do with machines like you would put gas into them or anything like that. It has nothing to do with vectors like what we've been working with in R or as a disease agent. It's just some terminology that the machine learners really like, so it's stuck. What support vector machines try to do when doing classification or regression is to dive into the training set and try to identify some sort of pivotal individuals that seem to help differentiate one class from another, or whose errors made by the model seem to be particularly important to minimize. So let's dive right into how the support vector machine framework works for classification. So one way to approach classification is to design what's known as a separating hyperplane, basically a flat boundary that is supposed to separate one class from another. For instance, in a two-dimensional data space, we might have two predictor variables, x1 and x2. Imagine we have two classes, the red class and the blue class. A separating hyperplane would be just any sort of line that neatly divides the data space into two, where all the red points live on one side and all of the blue points live on the other side. So the question becomes, all right, if we like this idea of doing a separating hyperplane, what's going to be the best separating hyperplane that we can invent? And so this is what's known as a maximal margin separating hyperplane that basically tries to maximize the distance between any member of one of the classes and what's known as the margin of the classifier. So what I've done is I've drawn a vertical or diagonal line here that separated the data space into two, and the dotted lines represent the margins. Now what you'll notice is that all of the red points are not only on the correct side of the hyperplane, but it's also on the correct side of the margin, the lower dotted line. Likewise, all of the blue points are not only below the separating hyperplane, but also below the diagonal dotted line. So what the maximal margin separating hyperplane tries to do is it tries to figure out the separating hyperplane so that the margin, basically the distance between the solid line and this dotted line here, is as big as possible, putting as much margin, as much of a buffer in between the two classes as possible. So when we work inside this framework, we actually notice that the maximal margin classifier here, its shape or where it falls in the data space, actually turns out to only depend on a few of the individuals. So looking back at the separating hyperplane and the margins associated with it, we see that the upper margin only passes through one member of the red class and two members of the blue class for the lower separating margin here. Now these three individuals are what's going to be known as support vectors. Why is that the case? Well, they're essentially supporting the separating hyperplane because their positions are the only ones that matter. You can go and you can move off any of these other points in other locations in the data space, and it's not going to change basically the location of the optimal separating hyperplane. It's only those points that the upper and lower dotted lines are passing through whose locations mattered in this problem when determining what that separating hyperplane looked like. And so they're support vectors. They're the ones supporting the separating hyperplane here. So that's a nice framework, and we can find that solution optimally very easily with mathematics if those two classes happen to be separable. But what if it's not the case? What if those two classes are mixed in a little bit with each other, which is usually the case here? So we can still use the framework of coming up with a separating hyperplane, but we're going to have to allow that hyperplane to make some sort of errors. So this is what's known as a soft margin classifier. Basically what we do is we propose a separating hyperplane, the solid diagonal line. We have the margins associated with it, the upper and lower dotted lines. And what we try to do is we try to come up with a separating hyperplane and margin scheme that allows for basically the fewest misclassifications possible. So in this case, the support vectors are the ones that are not only on the wrong side of the separating hyperplane, but also on the wrong side of the margin. So you'll notice that some of these red points here that are below the separating hyperplane are still starred as being support vectors. Same thing with the blue points over here. And that's because they fall inside, essentially, these upper dotted margin up here. So anything below this for the red points gets starred as support vectors. Anything above this for the blue points, the lower dotted line, gets starred for the blue class. These are all the support vectors in this case, and they're actually the only individuals that mattered when determining its form. So how could we do a soft margin classifier? Well, we need to give it some sort of leeway for making errors, because it's not going to be able to achieve perfect separation here. So one tuning parameter is this cost parameter C. It's kind of like a budget where we allow a certain number of misclassifications. So if this parameter C is bigger than 0, it's basically telling us that no more than C observations can be on the wrong side of the hyperplane. So larger values of C, smaller values of C, it's a tuning parameter that allows for more or fewer misclassifications, more complexity, less complexity in the model, etc. It deals with the bias variance trade-off. The best value for the cost parameter here would be determined by cross-validation, just like with any other tuning parameter here. So people have taken the soft margin classifier and ran with it, and it does decently for doing classification. But we quickly realized that this isn't going to solve all of our problems. Because what if there really isn't a nice linear separating hyperplane between the two classes? Even if there's a little contamination between the two, what if we run into a case like this where there's a clear boundary between the two classes, but the description of this boundary isn't a straight line? So what do we do here? Well, this is where the actual support vector machine framework comes in. And it relies on some really clever innovation called the kernel trick. Now, what the kernel trick does is it says, all right, in your original data space, there may not be a nice linear separating hyperplane. But maybe if we project the data into a higher dimensional data space, there will be. And what the kernel trick is interested in doing is projecting the data into a higher dimensional data space where it might be able to find a nice linear separating hyperplane. So exactly how does this work? Well, it's best shown through an illustration. Let's imagine that our data space is just one-dimensional. We have one predictor variable x here, and we have two classes. We have the blue class and the red class. We can see pretty easily that, all right, there is a well-defined boundary between these two classes. It looks like the red class has x values near 0.5 here. But there's not like a dividing line that we can say like x less than 0.5 versus bigger than 0.5 that'll do a good job in classification. Nothing's really going to work here. However, if we think outside the box and think in terms of two dimensions here, kind of add in this vertical axis, which doesn't really correspond to anything real, we see that we can actually come up with a nice separating boundary here that nicely separates the red class from the blue class. But how do we approach this mathematically? How do we approach this from an algorithmic point of view? Well, the way we can discover this boundary is to add in an additional predictor variable. So in our one-dimensional data space, we had information on the x variable. What if we let the second dimension of our data space just be x squared? Now, that second dimension isn't adding any new information because it literally is just the original value squared. But what if we go and plot the values of x versus the square of x? So we started out with a one-dimensional data space, just the values of x. We're projecting into two dimensions by having two predictors now, x and x squared, even though x squared is redundant. And what we notice is that if we plot x versus x squared here, now in this two-dimensional data space, there is a nice linear separating hyperplane. All of the blue points are above, all the red points are below. So it's a pretty remarkable way of thinking about the problem. Maybe the original data space just isn't good enough. Maybe if I add in new predictor variables to project the data into a higher dimensional data space, there will be some sort of nice linear separating hyperplane. All right, so how does this solve this problem here? Here's our data space of dimensionality 2, two predictor variables, x1 and x2, a clear boundary that we can see between these two classes, but a line is definitely not going to cut it. What if I added a third variable, x1 squared plus x2 squared, and projected the data into three dimensions? I have x1, x2, and now x3. Well, if I project this into three dimensions, here I have x1, x2, and x3 going up on the vertical, What I see now is that, well, actually quite remarkably, there is a nice linear separating hyperplane between these two classes. Basically, what I end up getting is that all the blue classes above this hyperplane, all the red classes below this hyperplane, and in this case, this added variable here that allowed me to project it in 3 dimensions was very cleverly chosen. So, you know that the distance away from the origin, the point 0, 0, would just be the square of the x1 coordinate plus the square of the x2 coordinate added together, then taking the square root. And we notice that, okay, this is a clever way of doing this because we see that the red points are basically close to the origin, the blue points are far away from the origin. So if we let our third variable just measure the distance from the origin, then sure, we can come up with a pretty simple rule. If that distance is less than 0.7 or something, then it's the red class. If the distance is bigger than 0.7, it's the blue class. So by adding in this third variable, projecting the data into 3 dimensions, we now can linearly separate those classes with a hyperplane. And so this is where the kernel trick comes in because, okay, what new predictors should I be adding into the data to correctly project it into the optimal higher dimensional data space where this separating hyperplane is going to exist? There's an infinite number of possibilities. We don't have time to go through and check every single way of doing this. So what the kernel trick does is it kind of figures out these variables for us. But it doesn't do so explicitly. It doesn't say, all right, you need to use the log of x, the square of x, etc. It does this implicitly, meaning that it's able to project into a higher dimensional data space without actually coming up with formulas for what these additional predictors are. So why can it actually do this? Well, it turns out that the equation for the optimal separating hyperplane doesn't depend on what the original values of the x variables are. Instead, it only depends on the distance between them, or the dissimilarity measure. So all we really need to specify is some sort of an equation that tells us, all right, how similar are individuals I and j. And so a kernel is just an equation that tells us, all right, if we're going to measure the similarity between individuals I and j, what equation tells us a number that defines that similarity? And the remarkable thing is, the answer to the optimal separating hyperplane in that higher dimensional space depends only on the equation that we give the kernel. So some kernels are going to be more effective than others. There are some popular kernels that tend to work pretty well, but that's the basic idea. So the basic idea is that with this kernel trick, we can just define an equation that tells us how similar two individuals are. By defining that equation, we implicitly define a whole slew of additional predictor variables that helps us to project into a higher dimensional data space with the hope that in that higher dimensional data space there will be a separating hyperplane. So it's all very trippy stuff. Good luck actually explaining that to someone else without really studying exactly what support vector machines are doing. If you're pressed for a nice simple explanation, basically all the support vector machine is doing is it's assigning a score to each individual, where the score is some number derived from transformations of the predictor variables. You can leave that unspecified. And essentially, if the score exceeds a certain threshold, it's class A, otherwise it's class B. All right, so a slide on some of the popular kernels for how you measure similarity, but it works, the remarkable thing. One of the more popular ways of doing this is with the radial basis kernel. Here's the raw data. Here's basically how the support vector classifier works. It identifies red versus blue class pretty well. We have another curved boundary, and it automatically discovers that there's a curved boundary there, and it's pretty neat. So support vector machines works for classification pretty well. There's a few tuning parameters that you have to choose, basically, that are related to that kernel matrix, and you'll learn more about those when you work through some of the problems in fitting support vector machines to data in R. So here's a good summary of support vector machines for classification. Essentially, our goal is to find a separating hyperplane, just a flat boundary, that is separating one class from another that might not exist in the original data space. But with the kernel trick, we can project our data into a higher dimensional data space where hopefully a nice linear separating hyperplane exists. If not, well, we can give it some sort of penalty for making misclassifications and basically come up to the optimal solution to our classification problem. And it turns out that the solution for where the separating hyperplane is ends up depending only on a few pivotal individuals in the data. We call those the support vectors. So one huge advantage of a support vector machine is that its solution is very sparse. You're able to store what the solution is, what that separating hyperplane is, with very, very little memory. A random forest, as you might have seen as you've been fitting these models, can sometimes take hundreds of megabytes of space to actually define what that model looks like. That's huge. For really big problems, a sparse solution that's only using a little information is very advantageous. All right, so what about support vector machines for regression? Well, when we do regression here, we're predicting numerical response. The idea is going to be kind of similar. The idea is that we do like multiple linear regression. We like that framework of basically assuming linear relationships between our y variable and our predictor variables. But we realize that in the original data space, with the raw variables that we've collected, linear relationships might not actually exist. There might be curvature, there might be other complexities. And so the idea is to once again employ this kernel trick to project our original data into a higher dimensional data space where linear regression might actually be appropriate. Now, the regression in that higher dimensional data space proceeds a little bit differently, but let me illustrate with an example. So here we have a one-dimensional data space because we just have one predictor variable x, and we have something we want to predict, our variable y. It's very clear that there's a high degree of nonlinearity, so a simple linear regression, a straight line, not a very good model for this case. What the support vector machine is going to say is it's going to say, all right, well, maybe not in this space, but in a higher dimensional data space, we'd actually do pretty good. So what if I added in, as an additional predictor variable in this case, x squared times the sine of x? Now, it looks like I just invented that from thin air, and I did. But notice when you plot x and x dot trans here, this new variable, we do see a really nice linear relationship between the y variable and actually this new variable that I've introduced in this higher dimensional data space. And so that's the idea. With the use of the kernel trick, we're going to try to stumble upon some higher dimensional data space where the relationship is linear, and that's going to be well modeled by a linear regression. Now, how does that linear regression work? It's a little bit different than least squares regression that we've been used to. Here's how the regression works in the support vector machine framework. Basically, the overall idea is that not all errors are going to count against the model. In least squares regression, we pick the coefficients, the form of the model, so that the sum of the squared errors, every single error matters, the sum of the squared errors is as small as possible. Not so with support vector machine regression. Basically, we invent some sort of threshold, we can call this epsilon here, and only errors that exceed epsilon count. So in this case, we have a bunch of errors that are within that threshold. They're not going to count against the model. The model is going to be found by minimizing the excess error above and beyond the threshold that we give to it. So these starred points are going to be the support vectors. These are going to be the 4 points whose errors matter when determining the form of the model. And so once again, we recover a fairly sparse solution. We use very few individuals in the data to actually come up with the form of that model. So the support vector machine is going to depend on a few parameters that we're going to have to tune. There's a cost parameter that talks about how much attention we pay to the errors the model is making. If we pay a lot of attention to these errors, then basically we recover least squares regression. We want to minimize the sum of all the squared errors. If we decrease the value of that cost parameter, then we give it a little bit more leeway. We say, okay, well, errors are bad, but we're not going to let it count too much against the model. And the resulting model is going to vary depending on what that cost parameter is. A very high cost, the resulting model is going to try to trace the stream of data points very closely. A low cost to making errors, well, we'll get some sort of wiggliness. It's not going to follow the data as well. But as you can imagine, with a lower cost, we're going to end up with a model that has a lower variance. It's going to be a little bit less sensitive to the particular set of individuals in the data, so it might generalize a little bit better. You have to figure out the right value of the cost with cross-validation. So support vector machines are available to you in R, and you'll get some practice actually going through how to tune them, how to make predictions with them, and they're a pretty neat way of approaching the problem, definitely unlike anything else that we've talked about before. So what are some pros and cons? Well, one of the pros is that they model nonlinear relationships really quite easily and with very little user input. With regression, it's a nightmare to come up with the right predictor variables to tackle nonlinear relationships. Another thing that it's doing is it's actually solving the problem that it's trying to solve. Given the cost parameter, the value of epsilon, it will find the optimal model for the data that's been collected on the training set. Same thing with least squares regression. It's actually coming up with the optimal solution to the problem. We can't say that with nearest neighbors. We can't say that with tree-based models. We don't really know the collection of rules or the collection of trees that actually gives the optimal solution to the problem. We're just coming up with something good. And so that's why a lot of mathematicians like this framework, is that you actually do come up with the optimal solution here. There are some cons. If you're doing it for classification, it's hard to get probabilities of being in each class. The predictions are more or less binary. There's no sort of statistics behind this, no confidence intervals, anything like that. And it can be very slow for big problems, but what isn't slow for big problems? All right, next up is neural networks.